We have talked about how a bond is polar or nonpolar, but what we haven't talked about is how a molecule overall is polar or nonpolar. So we're going to do that. But first, we need to understand that polar molecules will end up having an unbalanced charge. So there's regions of positive and negative charge, where a nonpolar molecule has a symmetrical balance of charge. So there is no poles. There isn't a positive region of the molecule. There's not a negative region of the molecule. Now this is best seen by filling out this table that we have here and looking at the different types of bonds. So if we look at HCl and sketch the ball and stick model, really I can just show you what HCl would look like right here. It'd be a hydrogen bonded to a chlorine, and you can see from that this bond here would be a single bond. And the bond itself would be polar because there's two different atoms bonded together, and each atom is donating an electron to be shared, so it is a covalent bond. So that bond is a single polar covalent bond. It's also pretty easy to see that this is a linear molecule with bond angles of 180 degrees. Now what's harder to see is whether the molecule itself is polar. And for that, you need to understand the differences in electronegativities between the atoms. So how we're going to do that is actually use our periodic table to look up the electronegativity values. And for hydrogen, it's 2.2, and chlorine is 3.16. Now that means that the chlorine is more attracted to the electrons in this bond. So the electrons are actually pulled closer to chlorine, making it more partially negative charged, and the hydrogen then, since the electrons are not around it, is partially positively charged. So we have poles that are created by these electrons being shared between the atoms. We can represent that the electrons are closer to the chlorine by drawing an arrow as our bond. So the arrow is pointing at the more electronegative atom. The electrons in the bond are being pulled to that more electronegative atom, and therefore this molecule overall is also polar because it has a region of positive and negative charge. So if we look at water, water is very similar. It has this bent or angular shape. These bonds here are single bonds. They are polar because they're between two different atoms, oxygen and hydrogen, and they are covalent because each atom is donating an electron to be shared. So like I said, this is a bent molecule, and the bond angles here are actually 104.5 degrees for anything that's bent like water. So when I draw this now, the oxygen is more electronegative than the hydrogens. So the electrons in both these bonds are pulled to the oxygen. So we can draw the bonds represented as vectors by drawing arrows that point to the oxygen. Therefore, the oxygen is going to be partially negatively charged, and the hydrogens will be partially positively charged. You have regions of positive charge and a region of negative charge in the molecule, so it is polar. And one thing that might make this easier for you to remember is that any molecule that is bent will be polar. When we look at CO2, this is what carbon dioxide would look like here. Carbon double bonded to two oxygens. Now, these bonds are double bonds. They are also polar because it's two different atoms, and they are covalent because each atom is sharing electrons to make these bonds. I think it's pretty easy to see once again that this is a linear molecule, and the bond angles for anything linear is 180 degrees. Now when we draw this one actually ends up being nonpolar even though the bonds are polar, because the oxygen is more electronegative than the carbon. That means the electrons in these bonds are being pulled towards the oxygens, and since both oxygens have the same electronegativity, the pull on those electrons is equal but ends up being in opposite directions. So an equal pull in opposite directions ends up meaning that we have no net area of positive and negative charge, and therefore the molecule itself is nonpolar. Now when we look at BF3, I can't make BF3, but this is something similar to BF3. It looks something like this, and you can see the shape of this molecule ends up being all the atoms are in the same plane, and it makes somewhat of a triangle shape. This is a trigonal planar molecule. The bonds in BF3 are single bonds, and they are polar because they're two different atoms bonded together, and they are covalent because each atom is sharing an electron. Like I said, this is a trigonal planar geometry, and those bond angles would be 120 degrees. Now the vector diagrams for these, if you look up the electronegativities, boron's electronegativity is less than fluorine. So we have electrons in all these bonds being pulled towards the fluorine atoms, and since each of the atoms are the same, the electrons are pulled in these bonds with the same sort of magnitude. So there's an equal pull on the electrons in all three directions, now towards the fluorines. Now if I were to add those up like a vector diagram, I would end up having no net result in a positive or negative charge, and this ends up also being nonpolar. Now, the interesting thing here is if I just change one of these atoms to something else, there would now be an unequal pull towards this atom, and that would end up making the overall molecule itself, therefore, polar. So things that are trigonal planar are going to be nonpolar if the three things bonded to the central atom are the same. It'll end up being polar if one of the atoms bonded to the central atom is different than the other two. Ammonia, or NH3, looks a little something like this. You can see these hydrogens are not in the same plane as the nitrogen, so we end up getting a ball and stick model that looks like this. These bonds are single polar covalent bonds, and the shape of this molecule is a trigonal pyramid, and trigonal pyramid bond angles are 107 degrees. So when we draw the vector diagram for this, nitrogen is more electronegative than hydrogen. So the electrons in these three bonds are going to be pulled towards the nitrogen. So it's going to be partially negative while the hydrogens are partially positive. And this time, these bonds will not cancel each other out because they're not in the same plane. Because they lie below the plane, these are not going to cancel each other out, and this molecule is going to be polar. And just like bent molecules, anything with a trigonal pyramid shape is going to be polar. So the last one we're going to look at is methane, or CH4. And this is what methane looks like when you build it. And the shape of this is called a tetrahedral. All of these bonds are single polar covalent bonds. And tetrahedrals have bond angles of 109.5 degrees. When I draw this now, carbon is slightly more electronegative than hydrogen. So the electrons are going to be pulled a little bit closer to carbon than the hydrogen. So the carbon will have a partial negative charge and the hydrogen's a partial positive charge. Overall though, if you took in the sum of all these vectors that you would draw in towards the carbon, these would all cancel out and the molecule itself is nonpolar. So very similar to trigonal planar molecules, any tetrahedral that has four of the same things bonded to the central atom will be nonpolar. But as soon as you change one of the atoms to something else, you've affected the electronegativity difference, and now not all the bonds are equivalent. So there will be a region of partial positive and partial negative charge, and this molecule would end up being polar.